Good afternoon, everybody. Welcome to this last episode of Getting Technical of this season. Today we are going to talk about nothing. Today we are going to talk about microns. And a micron, in the machining world, we like to talk a lot about micrometers and microseconds and things like that. And the moment we use the word micron, it's always related to quality. So today is about microns, and today is about quality. And as always, I'm not alone here. I have colleagues which are here to help me with this, to take care of all the magic with this session. And we talk about, as I said, microns. And a micron is nothing but chasing a micron, being it a micrometer or a microsecond, can cost a fortune. And we have to realize that whole discussion about quality and micron here and micron there is a matter of not only technical stuff. It's also a matter of money and time, And let's first put things a little bit in perspective. If we talk about a micron, a micrometer, normally what we talk about is on the level of chromosomes in the human body. That is what we are talking about. That is what 1 micron is. So if we have a discussion in the machining world, if machining people are standing together and they are talking quality and dimensions and stuff, and a micron more and a micron less, we should realize that what we talk about is very, very, very tiny. And if we talk about a microsecond, also here to have an idea what we talk about, a microsecond, if you compare a microsecond to a second, well, it's the same type of comparison like of a second within 11 and a half days. And people say then, 1 second compared to 11 days. That's nothing. Exactly, that's my point. A microsecond, if the discussion is about microseconds, and I think here on things related to machining time and time in contact and all those things we discuss in machining, be careful when you use the word micron and micrometer or microsecond. It's very, very, very little. And as I already said, it refers to quality. And quality, most of the time, when we talk about quality, there is that sense of, how should I say, a feeling of, is it all really needed? Because quality costs money and time. And there is that constant chase for cost reductions and increased productivity. So quality, but it costs money and it costs time. But you have to see it like this. Lack of quality costs even more. So it's not a matter of discussing how much quality costs or how long it takes to reach a certain level of quality. It's more a discussion of, if you don't have it, quality I mean, what is it going to cost you then? Being it in money or in time. And money and time is one thing, but quality or the lack of quality, it's a bit like that traditional comparison. People say it's like an iceberg. There's a little top of it above the water level where you see things, and then people say, when you talk about quality, lack of quality, it's about scrapped work pieces and rework that needs to be done and all that type of stuff. But lack of quality is so much more. To take one example, perhaps people are not always thinking on, delivering lack of quality, that's going to cost you image. Because if you deliver a workpiece which does not have the quality which was requested for, you are not only going to have a customer calling you and saying, this is no good, but you are also going to have a customer there perhaps starting to doubt about you as a supplier of workpieces or whatever you produce in your company. So lack of quality it's costing a hell of a lot of money, time, and so much more. So we better spend some attention to it. And if we talk about quality, there are in machining or in manufacturing in general, perhaps, there are two, how should I say, there are two families of quality. One refers to the process quality, to the manufacturing system quality. And that is when we start talking the process we use to produce workpieces, in our case machining, to which extent does it deliver what it is supposed to deliver? And that is correctly finished workpieces, and I come to that part within a second, but also correctly finished workpieces in the predestinated or in the pre-calculated time, and with the different cost factors related to it respected, and so on and so forth. And if we start talking about rejected workpieces, a percentage of rework, extra processing, all that type of thing, that refers to what I call the quality of the process, the quality of the production system. That's one family. Another family is the very straightforward workpiece quality. Are the dimensions correct? Is the shape correct? Is the surface roughness, the surface integrity? Are all the demands which are around the workpiece respected? Then we talk about workpiece quality, and the main subject of today is workpiece quality. But still, I want to mention a few words on production quality, process quality, because this is more about if you look to the process itself, the production system itself. To which extent does it manage to deliver without too many rejected workpieces, or without too much unexpected downtime, without too much problem solving time that is slowing down the process, all those type of things that in the end would influence the total cost picture, the total manufacturing cost, or the total productivity figure. Those things, that is what we refer to when we talk about production quality. Production quality is about how well do we spend our time? Do we spend the available time we have for production? Do we actually spend that as much as possible to produce correctly finished workpieces? That one could define as production quality. And if you look to the process itself, the technological side of it, there it's about how to which extent do we manage to run the process, the machining process, without too much unexpected things happening that would lead to unforeseen standstill. To which extent do we manage the production process, the machining process, that we don't break too many tools? That the quality of the finished workpiece is in line with expectation, that we have to stop the machine because there are issues with too long ships, all those type of things, that is connected to process quality, production quality. It's about mainly trying to avoid those things, or at least minimize, so that the available time on a machine is used to do what it is supposed to do, correctly finished workpieces. That in a nutshell. There's so much more to be said about this. If we talk about production quality, production system quality, a word that pops in my head instantly is what people refer to as manufacturing excellence or production excellence. Perhaps we could say production quality is a bit the same as manufacturing excellence, or I don't know. It's just something I put on the table here to think a little bit about. But as I said, the main subject of this session is workpiece quality. Now, if we talk about workpiece quality, we have to finish a workpiece or a batch of workpieces, and those workpieces, they are demands. There are demands about the dimensions. There are demands about the shape of the workpiece. There are demands of the different features or elements in a workpiece, how they are positioned compared to each other. There is the aspect of surface integrity, which is a very important thing in some types of industry. I'm thinking here mainly on on industry segments like aerospace, medical industry, where surface integrity is a very major thing. There is the surface roughness, surface flows, all those things. That is what we talk about when we talk about workpiece quality. And workpiece quality, what we have to realize is that it's an equation with quite a lot of variables. And if you try to rank the variables, at least in families, part of the quality of a workpiece will be depending on the tooling you use, the type of cutting tools and how you use them, and the cutting conditions and all that type of things. Part of the quality variables are workpiece variables. The workpiece itself, the material, the shape, the dimensions, type of material, as I already said, and so on. Part of the variables comes from the machine tools you use while they are cutting. How accurate can they move? How stiff is the structure? To which extent are the machines capable of to run without vibrations? All that type of stuff. A number of variables are also coming from machines, but machines while they are not producing. Perhaps a very strange family of variables, but what I try to put under that umbrella is when a machine is standing still, that is, for instance, perhaps because you are mounting a rough workpiece. Now, the accuracy with which you mount a workpiece is a variable, is an influencing factor for the final quality of the workpiece. And that accurate mounting of workpieces is something which is done while the machine is standing still. That explains a little bit what I mean with the variables in the family coming from the machines during downtime. The operator, a very important factor. Perhaps I should say the operator is not directly influencing the quality, but if things goes in the wrong direction, the operator is the person that should recognize that things are going the wrong way, that should understand why that is happening, and that should know what to do. So in that respect, an operator plays a very important role when we talk about total quality. Maintenance, that's what manufacturing management people very often refer to. Yeah, quality depends very heavily on maintenance, which is done. Most people think then in terms of maintenance of machine tools. I also would like to extend that to maintenance of cutting tools, maintenance of fixturing tools, all that type of stuff. And in the end, it's all the peripheral equipment around the machine tool, clamping, measuring, all that type of things that also will have an impact on quality. So if we talk about workpiece quality, there's quite a lot of variables we have to think on. And I have been talking now about process quality, and I have been talking about workpiece quality. And it's typically human to classify. Human beings, we always like to classify what is highest priority, what is not priority. Now, if you think on these two types of quality, workpiece quality or process quality, what do you think is the most important one? If there is a conflict, which one should be prioritized? Is what I mean here. Because sometimes there is that conflict. To reach a certain level of workpiece quality, you will have perhaps to sacrifice some process quality in terms of that you will have to spend some more time, that you will have to have some higher cost factors and so on. So put it in the comments. I'm always curious about this how people feel about this. Is it workpiece quality to the left? Or is it process quality to the right? What do you think is most important? And perhaps we should answer this question in an opposite way. What would be the consequences if we don't manage the quality? if we fail on having the needed quality, well, think of if you deliver a workpiece with a compromised quality thing, the result of it could be that the equipment in which that workpiece is used, could be an airplane, fails to function. And if an airplane fails to function, yeah, we all know the consequences. If, however, the process fails and for instance, the tooling costs go out of what was determined, yeah, okay, yeah, that's it. It's very unfortunate, but there is no more. So if you have a situation where the question is raised, what do we put as a priority, workpiece quality or process quality? What do we put up first, technology or organization? I think technology, workpiece quality is highest priority, should be highest priority, if you think on the consequences. If you think, as I said, I answered this a little bit in a negative way, what would happen if I don't have the quality I need? Workpiece quality, the main subject here. As I already said, workpiece quality, there are quite a few things we should talk about then. You have dimensions, tolerances on dimensions, you have the shape, you have the position of certain features on a workpiece, surface integrity, surface roughness, surface flows, and there are quite a lot of other elements also, like burrs which are formed, exit burrs which are formed, micro burrs, all those type of things. And if we try a little bit to classify now, dimensional quality, shape quality, and position quality. With other words, do I manage to produce something, to machine a surface in such a way that it has the correct shape, that it is flat or cylindrical or whatever is demanded for, that it is where it is supposed to be, that's positional quality, and that it have the dimensions we ask for, within given tolerance bands, of course. That is this chapter. And if we fail here, what is important then is, okay, I did my machining, I check the result, I see the result is not in line with expectations, so I need to correct. Well, the main reasons, I don't say the only reasons, but I say the main reasons if you have issues with dimensional shape or position quality is the machine tool itself, and or I call it CAM here, how you determine movement of cutting tools over or in a workpiece. Now, I'm pretty sure quite a lot of people now throw their eyebrows and they say, wait a second, and what about this and what? I know, but mainly if you have big issues here, it's about machine tool accuracy, stability, movements, and it's about how is the tool part of the tool. Is it accurate? Is it what is it's supposed to be to generate a certain form? Surface integrity. Now, surface integrity and surface roughness, I always have a bit of a problem here, because depending on who you ask, for some people, surface integrity and surface roughness are two different things. For other people, surface integrity and surface roughness, one is part of the other. So for the moment, let's keep them together. If we have issues there with surface integrity, surface roughness, surface flow, the main reasons that if we have issues is the machining process itself. The phenomena happening during machining are as such that the machine surface is not in line with expectations, and or closely related to it, it's about the cutting edge geometry, or the cutting geometry, I should say. And don't worry, I'm going to come back to that directly, but here it's very clearly, if there are issues with this, if we look at the machine surface, if we are unhappy due to the integrity, the surface roughness, or certain surface flows we see, Here we have to look at the machining process and see what happened and where it went wrong, and or the cutting geometry of the tool we used. Now, surface integrity is defined as it describes the properties and the condition of a machine surface with regards to the surface itself and the subsurface, the part just below the surface. And here, as I said, some people say, that's why I put it here a little bit lighter in color. Some people say, yeah, the shape of the surface topography is part of that, because it's the condition in which a machine surface is. And there are things to accept that. But personally, I feel more to say that surface integrity as such relates to the material. The material which we see on a surface, the material which we see just below the surface after being machined. Did we change the structure? Did we change certain properties of the material? Did we leave certain stresses or tensions in the material? Did we add or did we modify the composition? All those things, that is what for me is surface integrity. Surface topography, surface roughness is a different thing. With other words, if we talk about surface integrity, it's more a metallurgical thing. It's looking into the structure of a material after it has been machined and evaluating if the surface material or the material just below the surface has been changed, and if the changes are acceptable or not. This is the domain, and some of you are most probably familiar with it, where people talk about that after machining there is formed a white layer or a black layer, or the heat affected zone in a surface. Very typical. You find this type of discussions with people in for instance, the ball bearing industry. People in aerospace, they talk about these things. The medical industry, where a workpiece is going to be put in a human body, and then the material as such is an important thing. That is surface integrity. And then you have Burrs, which is quite an important thing in machining. There are different types of, but this is a subject on its own. I just want to mention it here. Surface burrs which are formed during or after machining. Also here, if you are aiming for what people refer to as burr-free machining, so no burrs are being formed during machining, and one could say, yeah, what's the big problem here? If a burr is formed, an exit burr or something, afterwards you remove it. End of story. Now, be careful with that, because if you look into that very simple thing, deburring, burrs are being formed during machining, you have to remove them afterwards, which is referred to as a deburring operation. A deburring operation costs money, takes time. I once had a case with a customer, and the production manager there told me that deburring as such stood for 20% of the production costs. And then we talk about serious stuff. Now, if you are in that case, if deburring is an issue, there are two ways you can work. You can say, okay, I have to be more efficient in my deburring, or you can say I have to change my machining process as such that no burrs are being formed during machining, or at least less burrs are being formed. Then we talk about that deburring technology, which more and more it becomes a discussion point nowadays. Burr formation is very clearly the machining process itself, and also the cutting geometry of the tools you use. That are the two things we need to discuss when we talk about Burr formation. But let me go back to surface roughness, surface flows. As I said, some people consider it as part of surface integrity. Me personally, I feel more to call it a chapter on its own. And to understand fully surface roughness and flows in a surface, we need to dive in a little bit more in a machining process related to the workpiece material which is being machined. And you see here two videos demonstrating two types of machining processes. To the left, you see a machining, to the right, left, yeah, you see a machining process in steel type materials. You know, the classic approach, the traditional approach. We see machining taking place here. We see a tool is pushed through workpiece material. The material is deformed. It's shorn off, evacuated under the form of a ship. And the red dotted line represents kind of the machine surface. And what we see is that that surface is rather smooth. To the right, you see a bit, I would say it's a but it's not really a simulation. It's actual machining you see there. But what I try to simulate there with this video is how machining takes place when you have high strength type of materials. Typical heat resistant materials, high strength, Inconel type materials, a machining process leads to that there is a certain deformation taking place under the cutting edge line. The cutting edge line that kinds of represent the machine surface. And what we see then is that due to the nature, due to the properties of certain materials, the workpiece material itself is being deformed below the surface, and that deformation leads to different properties of the material. Now, this is a very simple thing. This is acceptable or not acceptable. If it's not acceptable, and here we talk more about surface integrity, then we need to do something about. So the phenomena I try to draw your attention on here is having a high impact on surface integrity, surface flows. Certain parts of a surface can look a bit awkward when this takes place. This will influence Burr formation. That is what we have to think about here. Very strongly connected to this phenomenon. And people would ask me, yeah, okay, you talk about high strength materials. Why high strength materials? What makes them different from others? Well, that's a strain hardening tendency of those materials. If you look to machining, machining is a deformation process. You deform material until it shears off, but that deformation of material, what I try to visualize here with this little movie, you see just below a cutting edge that the material structure is being deformed. What you see here as a photo. The photo you see right now is Inconel 718, the machine surface, and just below, and you see how the structure is being deformed, and that deformed structure leads to I'm not going to say a different material, but at least leads to a zone in the machined material just below the machine surface where the properties are different. This strain hardening tendency we see in a number of materials. Temperature is a catalyst for this. So if we dive into this situation, the whole discussion we have in machining about should we use cooling, no cooling, all that type of things very much relates to this aspect in machining. When we have strain hardening tendencies, which we find quite a lot in high strength materials, heat resistant materials, the whole discussion about cooling, no cooling, which type of cooling is a very important one. Another thing to remember, and again, I use two videos to try to illustrate what we talk about here. If I take my traditional material, which is steel, what you see here to the left is so-called hard materials, hard steel. And what you see to the right is the softer materials. The video you see actually is aluminium you see being machined. when we see that the hardness of a material increases, we see that the relative movement of a cutting tool is let me say, not smooth anymore. It moves a bit randomly, and that movement, that relative movement, is going to affect the form of a surface. If you machine softer materials, the example here is aluminium, and if your cutting conditions or your cutting geometry is not what it should be, and you end up, for instance, in a situation where build-up edges are being formed, what you see happening here on the video, again, you see that the machine surface, just below the dotted red line, the shape of it, the form of it, starts to be very irregular. So, hardness of workpiece material, softness of workpiece material will have an impact on surface roughness, surface flows, and burrs. Also, of course, some other quality things will be influenced, but these will be the main ones: surface roughness, surface flows. With other words, if we talk about surface quality, if we talk about workpiece quality, the material aspect is always there to take into consideration. Whatever we say, we always have to talk with two words, and if we define a certain principle, if we say this and this and this, what we always have to mention is this and this and this in this type of workpiece material. Now, surface roughness as such, what we talk about is actually the form of a surface a bit on micro scale. That is surface roughness. Some people refer to it as surface finish. I never know what I should say. Is it surface roughness or surface finish? But I'm pretty sure you all know what I'm talking about. Now, the exact profile, if you would take a microscope and you would look, what is also referred to as the primary profile, that primary profile, part of that profile is the so-called waveness profile, which is considered, if there are issues about that, which is considered as a form quality thing. The waveness profile is coming from the machine tool itself, the stiffness, the stability, all that type of stuff. Now, if from the primary profile you deduct the waveness profile, with other words, a bit what you do, you take the exact profile and you take two parts and you pull. So you straighten the waveness profile. By doing that, what is left is referred to as the roughness profile. Now, if we talk about surface roughness, surface finish, what we talk about is the roughness profile. So it's the primary profile from which is deducted the waveness profile. Now, there are quite a lot of methods and systems to use this. People talk about the RA value, RZ value, RQM value. It's different methods, different systems, different approaches to define how we measure the roughness profile. If you enter here discussions, it's always a little bit difficult to know what exactly are we talking about. Never ever forget that the unity we use, if people say RA should be 1.6, we talk about 1.6 microns then, and you remember from a couple of minutes ago, microns is very little, so be aware of what we talk about here. But anyway, what you see here are two examples of a surface with the same RA value, yet the surface, if you look at it, looks completely different. So I give this as an example to show you relativity of things. RA in different types of applications, an RA value after turning, after milling, after drilling could be completely different types of surfaces. So again, if we talk about an array value, we should talk about an array value in relation to an application, turning, milling, whatever, and we should talk about an array value in a certain type of workpiece material. Now, traditionally, what people use here is a geometrical approach. They say, I have a tool with a certain nose radius, point radius. I move that tool with a certain feet over a surface. I leave kind of a curved surface behind, and that we define as the roughness profile. And that roughness profile, there are all kinds of methods or approaches to work with that. You can do mathematical, what you see here in the middle, with some simple formulas or more complicated formulas, whatever you want. Or you can work with a more pragmatic, with tables or diagrams, where we say, okay, there is a certain relation between the point radius, the feet, and the surface roughness. And it's all very nice, very well. And if you compare then this model, this concept with surface roughnesses to calculate them, and if we apply it in reality, and if we measure it, what we see is there is a certain window in which those things calculated and reality are more or less in line. But if you go with feeds, the example here referred to feeds, the horizontal line is feeds, the vertical line is array values, measured, the red line, blue, calculated, the blue line, sorry, is calculated. But what we see then is if the feeds are higher than what we define as the application window, that the measured array values are below the calculated value. The surface is better than what we expected with higher feeds. With lower feeds, it's just the opposite. And then the question, of course, is, yeah, but can't we modify this model? Can't we make this more accurate, this concept? And yes, we can. But for that, we have to be aware of that roughness is more than a tool with a radius that moves with a certain feet. Because if you do that type of approach, we talk about what academics call the nominal kinematic roughness. The roughness with a nominal tool, a standard tool showing no wear, no vibrations, no nothing, a theoretical cutting tool that works in a workpiece and moves with a certain speed, the feet. But the reality is that is only part, because next to that you have the cutting roughness, as it is called, the cutting roughness, and I'm going to mention it directly, that relates to the roughness that appears due to the cutting process itself. And you have, of course, additional factors. You have micro vibrations, you have ships that are hitting the surface, and so on. Now, those things, we can call it surface flows. Surface flows are irregularities in the surface. You find it here and there at random places. It could be pits and cracks and scratches and burrs. Burrs coming from ships hitting the machine surface. Scratches. It can come from the actual shearing off of the material. If the shearing off goes below the cutting line, that will influence how a surface looks. It can come from side flow effects, what you see here. The little red thing that moves sidewards compared to a cutting edge is going to affect how a surface looks. So all these things, being part of a machining process, are going to influence the actual surface, the workpiece material. What I try to illustrate here, on top you see the theoretical, a point with a radius moving with a certain feed leads to a certain roughness profile on a surface. But if you have certain materials, the example here is the somewhat softer materials, but there will be microburrs formed, and those microburrs will affect the surface roughness. So cutting roughness is about how is the shearing off, is there side flow, is there build-up edge? All these types of things is what we need to take into consideration then. And those things are mainly influenced by cutting temperatures and cutting speeds. A bit the same thing in this context. And what we see here, and the diagram shows on the horizontal line the cutting speed, the vertical line again is RA values. The red line gives us an idea how the surface roughness would be if I have one tool in one material and I use different types of cutting speeds or different cutting speeds. And what we see then is that when cutting speeds are too low to the left, your surface roughness go up, and there is due to build up edge formation. When your cutting speed is too high, however, you also start to have surface roughness that is deteriorating, RA values that are going up again, and then it's due to side flow effects on the point of a tool. So cutting speeds are important, wear patterns, because we all consider a new tool when we make this type of considerations, but we all know after a while a tool shows some wear, and that wear is changing the geometry, the form of a cutting edge, the cutting point, and that of course is going to influence how the surface looks, the machine surface after a while. So machining time, wear we need to take into consideration. The feet, perhaps a very major one. What you see here is each time the theoretical value, the red dotted line represents for a certain tool with a certain feet, what should be normally the theoretical surface roughness. The black line shows the surface roughness measured after one workpiece, two workpieces, three workpieces. So the horizontal line kind of represents timing cut. How long has the cutting edge been cutting? And what we see then is if I double my feet, double feet leads theoretical to double surface roughnesses, the dotted line. If I take the feet again double, again my theoretical surface roughness, the dotted red line, will double. But if I look to the black lines, the measured ones, we see a very intriguing, very interesting phenomenon here, and that is the higher the feet, you remember a couple of slides ago, the higher the feet, the more we have a situation that the surface roughness, the measured surface roughness, will be below the calculated one. And you could take this diagram as such. If you use a small feet, and if you have 10 workpieces, and if your demand is a certain surface roughness represented by the dotted red line, where a number of workpieces will be correct and a number of workpieces you will have to reject because the surface roughness is above what is wanted. If you take the situation with a very high feet, all workpieces are acceptable in surface roughness. So reliability of the process, and here we touch on process quality, of course, is higher when feeds are increased. Tool geometry, I take the example of secondary cutting edge geometries, wiper geometries as some people call it, scraper geometries is another word. What we see here is if an example for a turning application, if you have a cutting point with a scraper geometry, what is shown here to the bottom right, a scraper geometry for the same tool with the same cutting conditions generates a surface which is much better concerning surface roughness considerations. Just as an example. This was very fast. Quite a lot of things we talked about. We discussed about process quality, production system quality, where we say basically what we talk about here is to which extent do I manage the process, do I have things under control so it leads to the wanted result, a correctly finished workpiece. That is priority one always, correctly finished workpiece within the determined time and with the pre-calculated costs. If we fail there, that is then we have an issue with process quality. Workpiece quality, which was the main thing here, and remember here we talk about dimensions and shape, position, surface integrity, roughness, and so on. And again, careful, surface roughness, we talk about micrometers. In the beginning of my presentation, I had kind of a waving finger here. Be very, very aware of what we discuss here when we discuss a micron or 2 microns or something. The same for microseconds, for that matter. I always like to see time calculations where people start talking about milliseconds and microseconds. And then I think, do people really appreciate what they talk about? But okay, that's another discussion. Very important. The core, what I tried to say here is that if we talk about surface roughness, something which is directly related to a cutting tool, see things correctly. Go beyond what we refer to as the nominal kinematic roughness, the roughness which is theoretically generated by a point with a radius that moves with a certain feet in a certain workpiece material. It leaves that curved surface, and we say that's the surface roughness. Now, it's not as simple as that. You have the cutting process itself. There are certain phenomena taking place, influenced by the geometry of the tool, influenced by the workpiece material, influenced by the cutting temperatures, and all those type of things that, on top of the kinematic roughness, will also influence how the surface looks. And next to that, of course, there are all those other factors like ships scratching on a surface, micro vibrations that makes that a tool starts to move in an irregular manner, and so on. So the whole thing with surface roughness, especially when you bring it down to micron level, is a rather complex subject in machining. Now, to simplify life a bit, a smart way to approach surface roughness, I always say, is and I give it here with an example. Let me first explain the graph you see. You see on the horizontal line 4 different types of tools with 4 different types of nose radiuses. A nose radius 0.8 to the left, and then it's going up 1.2, 1.6, 2 millimeters nose radius. For every nose radius with the different colors, you see different feet being used. So every bar here in this diagram is a combination of a nose radius of a tool used with a certain feet, and the vertical axis is the surface roughness then. The RA value is the unit we use here. And what we see very clearly is for one nose radius that if you increase the feet, the surface roughness go up. If you take 1 feet, let's say a feet of 0.17 millimeters per revolution, the brown bar here. For 1 feet, if you increase the nose radius, the surface roughness goes down. The surface roughness improves. Now, these two things, if you combine and if we try to focus a bit, leads to that we can make a statement. If you have a tool with a certain nose radius, whatever nose radius, depending on which surface roughness you need to respect, you need to achieve, the feet selection is very important, and the general rule is the lower the feet, the smaller the nose, the better the surface roughness will be, at least in theory. Please bear in mind all those little other things I have been talking about here, like side flows effect, deformation zones that go under the cutting line, and so on. All those things needs to be taken into account also. And if you take those things in account, you have a blue line that I want to draw in this diagram, a blue line that says, if you have an opportunity to select a cutting tool with a bigger nose radius, you move on the horizontal line, on the horizontal axis from left to right. The higher the point radius, the higher the nose radius, even with high feeds. And we like high feeds because high feeds are very favorable for a smooth cutting process. The more you will have a nice balance between high feed and good surface roughness in a reliable manner. So surface quality, surface integrity, surface roughness directly related to a machining process is a matter of a bit juggling different things at the same time. It's more than just what's the nose radius. It's more than just what's the feed. It's how you combine things that is truly the secret of achieving good results. I said a micron costs $1 million. A micron is 10 minus 6 exponent, and $1 million is 10 plus 6 as an exponent. A micron is very little, but chasing it could cost $1 million. I'm not pleading here for neglecting quality. I'm just saying let's all be very much aware of what we talk about. With that, I'm where I wanted to be today. Let's check about questions. I'm pretty sure this subject, there are quite a lot of questions. There are always lots of questions. That's indeed quite a lot. I try to answer as many questions as possible here today. The questions I cannot answer today, I come back tomorrow or the rest of the week and I answer them in comments, or you can send me an email or if you want, and we can have a more in-depth discussion. But anyway, there is a question, how would one qualify that surface roughness and surface integrity are different? Personally, I always say surface roughness is a geometrical thing, while surface integrity is a material structural thing. Now, I do realize that way of putting it, there is always a gray zone where the two are overlapping. So I would say, if in a smart way, in an intelligent way, if you discuss one, you should always have in the back of your head the other also. They are different, but to a big extent overlapping. A next question is about, is flatness more of a machine tool and fixture function rather than a cutting tool design and wiper geometry? Yes. However, again, one of those things, flatness after machining relates to the stability of a machine tool. Indirectly, however, if you selected a cutting method that leads to high cutting forces, but high cutting forces will be a bigger challenge for the stability of a machine tool than lower cutting forces. So flatness relates to stiffness of a machine tool. Indirectly, however, if you feel there is a lack of stiffness in a machine tool, you should modify your cutting process, you should modify your cutting geometry as such that you lean less on the stability of a machine tool. The next question is about, does this approach changes when you are micromachining? No. The values will be different. The windows of applications of certain equations, certain models will be different, but the general phenomena we were talking are the same. Then there is, I don't know if it's a question or just a statement. Are we hunting for tolerances, or are we hunting for parts that works under most expectations? I like the question. I see it like this, and I trust now the designer of a workpiece knows what he's doing. although there can be asked questions about people working with too high safety things and so on. But let's say if on a drawing a tolerance is giving of plus minus 1/10, just as an example now. So the moment you do machining and the result of your machining is within that tolerance field, and again, I suppose the designer knows what he's doing, that is okay. Then it's fine. Now it's deep in the genes of a machining person. I I suffer a bit from that also. Is that if it says 100 plus minus 1/10, that the machinist is going to strive for 100. And then of course things goes wrong. That is what I said with chasing a micron can cost 1 million, because if you chase something just to prove to yourself or to colleagues, this is what I can do, when it's not needed, yeah, then it's a bit a waste of money and time, of course. So if the designer knows what he's doing, and if a workpiece has the quality which is demanded for, that's good enough. Doing better than what is asked for is just going to cost money and time. I don't know if that gives an answer. The time, yeah, okay, we have some time more. Why is there a difference between calculated and measured surface roughness? But that is what I explained when I said normally when we talk about roughness, people always refer to the kinematic roughness, a tool with a radius moving with a certain feet. However, the roughness is more than that. The roughness, part of the roughness, also comes from the cutting process itself. And that cutting roughness, as we refer to, the lower the feeds, the more that will become bigger and bigger compared to the kinematic roughness. That's why we see that with bigger feeds, theoretical kinematic roughness and measured kinematical roughness, the bigger the feed, the closer and closer they come together or to each other. And even from a certain point on, if you can increase your feeds even further, high feed machining or something, you see that the measured surface roughness will be even better than the calculated one. So it's not about to improve the model. The model is okay, but the model needs to be extended. What is an exit burr? An exit burr is a burr which is formed at the moment the cutting edge leaves the workpiece material. In case of milling, there it's easiest to understand. You have a milling cutter, it's turning around. Cutting edges are starting to cut, are cutting, and somewhere they stop cutting. Well, where cutting edges leave the workpiece each time again, every rotation, and if a burr is formed there, that is called an exit burr. Another question is side flow happening in all materials? Yes, side flow is happening in some materials more than in others, but side flow is always happening. And yeah, it's very strongly depending on the cutting conditions also you use. Okay, I see we reach end of the time. The remaining questions, I take care in comments afterwards. As I said, if you have more questions, please put them there, and I'll take care of them afterwards also. For me, it's time to close this session, to close this season also, because now we stop for 2 months. We go in summer recess, but in September we are back, and then we start the third season. I'm hoping that this session, and I would say perhaps all the sessions we had in this season, were interesting for all of you. If some of you lying on the beach getting bored a little bit and are thinking on this, remember all these principles are coming, or all the things we talked about, they are also available in the different technical books we have, which you can of course ask for, and then we would gladly send you some copies. So if you are laying there on the beach and don't know what to do, you never know, then you have some useful reading. Anyway, during the summer, enjoy your holidays. And personally, I'm looking forward to see you all back in September then, when we start with the third season of these type of events. In the meantime, if you have suggestions, questions, if you think it would be nice to hear something about this or that related to machining processes or machining production systems, please let us know. With pleasure, we try to fit it in and make it even more interesting for you. Thank you very much. Enjoy the summer holidays and looking forward to see you all back in September.